So I'm glad to talk about this work about how to use a machine learning or deep learning technology to enable the self-organizing radio access network. So this work has been done when I was intern with Samsung in the last year. So let's get started by taking a look at the problem statement. So usually we hear about those complement in our life. For example, the connection is too slow, or say, excuse me, I cannot hear you, or this web page cannot be loaded at all. So behind those kind of problems, there could be a lot of root causes. So for example, excessive up tilt or down tilt, coverage hole, too late handover, or inter-cell interference, excessive cell power reduction, cell overload. But usually it's not straightforward to diagnose those root causes. Currently, the existing solution is at each cell, we can monitor the key performance indicators, those KPIs. And then if any anomaly KPIs has been detected, then the network engineers will spend hours of efforts to figure out what is wrong there and try to fix them. So here we're asking, can those network operators automate this diagnosis and self-healing process? So based on this problem, we have a few system challenges. So first, how to predict those anomaly KPIs before any fault really appear. We don't want to wait to process those faults when they really appear. And then how to figure out the root causes based on those thousands of cell KPIs. And also, how can those systems can self-recover from any fault? And also, in terms of the TB level cell KPI data, how can we deal with that? Those are the system challenges we need to consider in this work. So in order to solve those system challenges in this work, we propose this four-step closed loop to address those system challenges. So first, in the very first step, at each cell, we try to monitor those thousands of KPIs in real time. And then we move to the second stage, anomaly KPI prediction. So we try to predict if any anomaly point will appear based on the historical KPIs. So if we can detect any points, look, for example, this two, that's either higher or lower than a threshold, then something might be wrong. So we need to move to the third stage to detect what is around there, what is the root cause analysis, by perform the root cause analysis. And then we move to the fourth step for the self-healing. So in this step, we would like to the network to self-recover from the fault. And then we make these four steps as a closed loop. Also, in order to deal with the TB level data, we also introduce the Apache Spark and Apache HBase. So Spark is a real-time streaming processing engine, and HBase is a real-time database. And in today's talk, we will focus on these two components, anomaly KPI prediction and root cause analysis. So before we talk about the detail about these two components, let's first take an overview of our data used in this work. So in this work, we took a real-world data from a US cellular operator. We have two components of data. First is the aggregated cell data set. It involves around 100 cell KPIs, for example, mobile subscriber count, attach count, and so on. And this data has been collected in around 9 months within 1 hour as an interval. And also, we have a non-aggregated cell data set. It involves around 4K KPIs that has been collected in around half an year. But here it has been collected with 15 minutes as interval. So for those 4K, more than 4K KPIs, we further divided to those subcategories like accessibility, returnability, integrity, availability, mobility, and so on. And here we show a few examples about KPIs like interference power average, interference power total, and so on. And then let's talk about the first component, anomaly prediction. So the objective is pretty straightforward here, is to predict the potential anomaly KPIs or events in the future, just based on the currently or historically recorded or reported cell KPIs. So to do that, we consider a few system challenges here. First, we need to identify related KPIs. So in particular, which means given a predictive or target KPI, we need to figure out what are the which KPI are related from those thousands of KPIs. And then inter-cell interference. So this fault may not just come from a single cell. It also might be the interference from multiple cells. We need to identify that. And third system challenge would be the real anomaly events. So if we take a look at this historical example data, we can see there are just 2 anomaly points over this hundreds or thousands of points. We need to let the system focus on these 2 anomaly points. So to solve this system, the first and the second system challenges, we first need to select a proper model to do that. So usually we have a few popular models like CN, which is good at extract the special features, but usually it may ignore those time series relations. And then RNN or LSTM. So this vanilla type RNN or the LSTM, they are good at to extract those time series data, but usually it do not that work to extract those special features. So in this work, we consider we are using this convolutional LSTM that is good at to extract both temporary and special features. So this model, it takes those thousands of historical cell KPIs as an input and also output the value of a target cell KPIs. And this model shares a lot of similarity with LSTM, but it has but the key difference here is it replaces all the production operations, as you can see here, to those convolution operations. Those are the key difference between this convolution LSTM and LSTM. So this replacement enables this model to extract the special features. And then if we think about the third challenge, unbalanced data set, where we have a very well-run anomaly events. We take 2 tricks here. The first one is a data undersampling. That's a very frequently used trick. Try to discard the redundant data that is far from the anomaly points. For example, in this case, we can just cut down the middle data. And the second trick is the penalized classification. So we try to introduce significant more cost if we incorrectly classify an anomaly point as a normal one. So we can focus the neural network to put more attention on those anomaly points. So to do that, we can try to adjust the weight here for both anomaly class and the normal class. So in this case, alpha will be much smaller than beta. And then we will move to the next part, root cause analysis, once we identify if there is any anomaly points here. So here, the system challenges mainly about those root cause labels are usually not available for supervised learning. For these two reasons, the first, those network engineers usually do not deliberately to attach those resulting fault to the logs, and also it would be too expensive to collect the logs by purposely to introduce those faults to the cells. In this work, our solution is we first try to generate the synthetic data set with NS3, that is a network simulator. And then we try to employ unsupervised clustering by removing those fault labels. But here still, we can still use those fault labels to evaluate the performance of our unsupervised learning algorithm. And if it works good, we can apply this model or algorithm to the real-world data set. So here I'll give a brief overview about how do we make this NS3 simulation. So first we will try to generate a normal topology, look like this, and then we randomly select X cells, look like this 4 out of n out of them, and for each fault cell, we try to randomly assign a certain fault case to them, and then we run the simulation to collect the KPIs, and also we can assign the fault labels to those KPI logs. So after getting those training data, we can apply it with on our unsupervised learning algorithm. Here is the simulation setup about how to configure the normal cell by setting the topology, carrier frequency, bandwidth, and so on. And also we will show here how to introduce each different fault cases by change the corresponding configurations. So here I'll give more details about the NS3 simulation. So in this simulation, we totally introduce 6 possible faults: EU, DU, ERP, intercell interference, delayed handover, coverage hole. And we totally have 30 cells, and we randomly select 6 out of them. And for each of them, we randomly assign each one possible fault to them. And in this simulation, we in total have 40 KPIs, and we perform the simulation in 1 hour duration. So after having this simulation data set, next we'll try to consider how should we apply the unsupervised learning upon the data set. So to do that, basically we have in our deep learning part, we have two components. First is autoencoder, and then after getting the output from the autoencoder, we will put that into a agglomerative clustering. So for autoencoder, it takes those thousands of cell KPIs as the input and try to find the key features from it. So as we can see here, the autoencoder has 2 parts, encoder and decoder. The encoder will try to compress a high dimension cell KPIs to a lower dimension, and then the decoder try to recover from the compressed one to the original part. So after the training, we will only keep the encoder part, and we'll take the output from the encoder to this next component. And then let's take a look at this part, agglomerative clustering. So basically, this is a bottom-up algorithm. So it starts from taking each each output or each feature from the encoder as a different cluster. And in each iteration, it tries to find two nearest cluster measured by the Euclidean distance or Pearson correlation distance. And after the iteration, it starts to converge to much less clusters. So finally, the remaining cluster number will equal to a predefined number. But one limitation for this unsupervised learning approach is it can only output, to make some data as in a cluster, but we still don't know the physical meaning of that cluster. For example, we don't know whether that cluster means a case of the inter-cell interference. So we may need the network engineer to infer that from the distribution of the KPIs. I will show more examples about that. After talking about the two main components in this closed loop system, then let's take a look at the evaluation part. First is the evaluation about the anomaly prediction. So here, the objective is to use the last 5 hours data to predict the value in the next hour. For example, in this case, we take this X2 handover failure rate as an example, but we can definitely apply this approach upon other prediction target. And in this evaluation, we use a real-world data set, as I mentioned before. To evaluate that, we take 4 deep learning models, CN, LSTM, convolution LSTM, and the combination between CN and LSTM. And to evaluate the performance of our algorithm, we try to consider the following performance metric, TP, FN, FP, TN, and also mean square error. So first, let's take a look at the prediction performance with different machine learning models. Here we consider this 4 models, and as we can see here, the convolution LSTM and the combination between CN and the convolution LSTM performs much better than the first 2, because the convolution LSTM itself can extract both temporary and special features from the original data set. And also we try to evaluate the effect by putting different weights over the normal class and the anomaly class. So here we try to apply different weights here. And as we can see here, if we assign an inefficient high weight to it, it will return us a low recall value. But if we excessively increase this weight, as in this case, the network will blindly classify any input as a normal anomaly KPIs. So that will doesn't make any sense. So it will be important to explore the trade-off between this anomaly prediction accuracy and the tolerance about the fault alarms to reach a balance point. And then we'll show the evaluation results about the root cause analysis. That is based on our simulation data from US3. It shows the clustering accuracy can goes up to 99.5% by using the autoencoder and agglomerative clustering. And as I just mentioned, there is a limitation about this approach. It's not straightforward to tell what is the physical meaning of each cluster. So for example, here we we show we show 7 key KPIs here and the distribution of them, and also we put the corresponding label here, the normal case and other fault cases. So the network engineers may need to infer what is the physical meaning, but since our final target is not to infer the root cause analysis, is not to perform the root cause analysis, but we want the network to be a closed loop system. So remember, we still have a last step named self-healing. So that in that step, we will try to use the deep reinforcement learning that can take the output from this step, which is unnecessary to specify the exact physical meaning of the cluster, and in that step, it can recover based on whatever input here. So I try to wrap up right up here. So in this discussion, we proposed a self-organizing radio access network system with a machine learning and deep learning technology. And also we implemented this anomaly prediction and root cause analysis components and evaluated by a real-world data set. And also we show our proposed method can achieve 86.9% accuracy for anomaly prediction and 99.5% accuracy for root cause analysis. So moving forward, we will try to continue and finish the last component, self-healing function with deep reinforcement learning, and make the whole system as a closed loop. And also we will try to better understanding how the KPI sampling granularity will affect the anomaly prediction accuracy. For example, here in this work we sample it with 50 minutes. But what if we reduce it to 5 minutes or even 1 minute? We know we will introduce more traffic, but will we have more better performance here? That's going to be a question we will answer in the future work. Yeah, thank you.